In order to draw the lowest energy conformation for branches on cyclohexane, you have to draw these cyclohexane molecules from the side. That's the only way that you can see which branches are axial and which are equatorial, and so then you can give the lowest energy conformation. Now, if you look back at the two positions, the axial and equatorial positions, the axial positions are really close to each other. The atoms in the axial positions are really close to each other, as opposed to the equatorial position, which is just pointing off into space. So all of these atoms, all of these hydrogens, have electrons in them, and so they repel each other. And if something is in the axial position, they repel each other a lot because they're so close together. They push on each other, and that adds to a lot of instability in the molecule. Whereas if you have big, bulky groups in the equatorial positions, well, those are just pointing out into empty space. So they're not really next to each other as much. They're less crowded. So the thing you want to take away from this is that bulky groups would prefer to be equatorial. They're more stable when they are equatorial because they have more space. A bulky group does not want to be axial because it has no space. It'll push against, and it'll feel the push of the other atoms too much. So, gigantic takeaway is that bulky branches are more stable when they are equatorial. Because there's more space around in those equatorial positions. Okay, so our first step in these, in order to draw the molecule so we can see the axial and equatorial positions, we have to draw the cyclohexane ring from the side. So we'll take this ring, and the way you draw cyclohexane from the side is you have two parallel lines. The one at the bottom goes a little further down, the one at the top goes a little further up. The side that points down, draw a dot going up. The side that points up, draw a dot going down, and then connect the dots. So there's our cyclohexane from the side. Now let's think about the branches. Now we have two branches, and they have the same bulkiness. They're both methyl branches. There's only one carbon in the branches. So there's no preference for one to be equatorial or the other to be equatorial. They're both the same size. Now we should set something straight at the outset. It doesn't matter how we assign these, but we should assign coming out at you as either being up or down. So for example, if we decide that coming out at us is going to be up, then going away from us is going to be down. We could have done the reverse. It doesn't matter, just so long as we're clear that something that's coming out at us and something that's going away from us has to be on opposite sides of this ring when we look at it from the side. Okay, so let's choose one of these. Let's choose one of these methyl groups. So this one right here on the left. And we've decided that anything coming out at us will be going up. And so we want this to be equatorial. Now, if we look at the carbons on the ends are the easiest ones to remember, because if an end is pointing in a certain direction, like this end is pointing up, the axial position there is up. If an end is pointing down, the axial position there is down. Okay. Well, we want to draw it going up. We want to draw this methyl group as going up. But we want to draw it as equatorial because that's the most stable position for these branches. Bulky branches are the most stable when they're equatorial. So up equatorial will only be on this left carbon. I'll get rid of these other branches. Those were just there as sort of guideposts. Okay, so that'll be this right here. I should say that. Okay, next, right next to it, on the carbon adjacent to it, we're going to have a branch going down. And if we go next door, if this carbon is equatorial going up, then next door, and it doesn't matter which carbon we go to, I'm going to go to the right here, next door the equatorial position will be going down because they alternate. Notice, if one is up, the one next door is down. The one after that is up, then down, up, down. They alternate. So, this is what the most stable conformation for this molecule would look like from the side. We would have the cyclohexane ring and two methyl groups pointing in opposite directions. Here they're coming out and going away. Here they're up and down. And they're both, in this case, equatorial, which is the most stable position for bulky things. All right, let's practice with B. So first, in order to show these stable conformations, we have to draw this cyclohexane ring from the side. So to draw a cyclohexane ring from the side, you want to put two parallel lines. The line at the bottom goes a little bit further down. The line at the top goes a little bit further up. The side that's pointing down, put a dot going up. The side that's pointing up, put a dot going down. And then connect the dots. So that's our cyclohexane from the side. Now let's think about the branches. We want to look for the bulkiest branch. Now we have two branches here. We have this methyl branch. There's one carbon there and it's a branch, so YL. One carbon is the prefix for that is meth, and it's a branch, so YL, methyl. And this was one of those weird branches, one of the branches that have branches, and the name for this was isopropyl. So the isopropyl branch is the bulkier one. And it's very important that the bulky things are more stable when they're equatorial. So here we want to draw the lowest energy conformation. That's the most stable conformation. That has the bulkiest things equatorial. So the bulkiest thing here, the bulkiest branch here is this isopropyl group. We want to make sure that that is drawn equatorial. Now remember your guideposts. The side of the cyclohexane ring that is pointing up, that's where you have axial going up. The side of the ring pointing down, that's where you have axial going down. Those are just guideposts. I'm going to erase those in a second. We want to put equatorial, we want to put this isopropyl group equatorial. Now it doesn't matter whether coming out of this, whether this is going up or down. Just for the sake of simplicity here, we'll have that going down, which means if we had any dashed wedges, they'd be going up. We don't have any of those, so we don't have to worry about that. But just because coming out at us and going away from us, that's opposite directions, that means when we look at it from the side, they would have to be going in opposite directions. All right, so we want this isopropyl group going down. Well, we have our guideposts there in pink. If the axial group is going up, then the equatorial group is going down. Notice, if the axial group is going up, the equatorial group is going down. So, I can erase my guideposts now. We've taken into account the isopropyl group. And now we have to worry about the methyl group. So the methyl group is going to be right next door. Now, you could go in either direction. You could go back here or here. You'll get the same answer either way. It's the same molecule. I'm going to go in the front because there's more room to draw. So we want to draw a methyl group. And because it is a solid wedge, we want to draw it going down. But is the down position on this next door carbon axial or equatorial? If this carbon is equatorial down, then the carbon next door switches. This would be equatorial up. Every carbon has an axial and an equatorial position, so if that's equatorial up, then it has to be axial down. Right? If this is equatorial down, next to it is equatorial up, which means that you have axial going down. So we need this methyl group going down, so we have to draw it as axial. There's no way to have both of these branches equatorial going in the same direction next to each other. So we chose to have the bulkier branch equatorial. That gives it more space. What'll end up pushing against this methyl group are the other hydrogens that will be axial. There's an axial hydrogen here, there's an axial hydrogen here, and so those will push on this CH3, and that's what gives rise to the instability. But there's at least less instability than if the isopropyl group were going axial, because that's bulkier. Okay, and so that would be the most stable conformation for this molecule. Now let's try this next one. So they're asking for the most stable conformation. The first step is just to draw this cyclohexane ring from the side. To draw cyclohexane from the side, you draw two parallel lines. The one on top goes a little further up. The one on the bottom goes a little further down. So the one on top goes a little further up. The one on the bottom goes a little further down. The end that goes down, put a dot going up. The end that points up, put a dot going down. And then connect the dots. So that is cyclohexane viewed from the side. All right, now we have to just decide whether a solid wedge will be up or down. We could choose either. I'm going to choose that a solid wedge will be going down. Either way you choose, you'll get the same answer. It may not look exactly the same as the one that I'm drawing, but it will be the same molecule. If you remember, these are three-dimensional, and the molecules can rotate around. You'll be able to rotate your molecule in a way that'll make it look like mine. So if the solid wedge is going down, then the dash wedge is going in the other direction, which is up, right? Because this is coming out at you, that's going away. Those are opposite directions. So if we look at it from the side, they'll also have to go in opposite directions, up and down. All right, so we've drawn our cyclohexane ring. Now let's think about these branches. All of these are actually around the same size. Chlorine is pretty big. Chlorine is about the same size as a methyl group. So a CH3, if this is a branch, CH3, that's about the same size as a chlorine atom. It's a very big atom. I should maybe more like that. So they're about the same size. So these two chlorines in the methyl group, those, it's not about which one is bulkier. What we want to think about in this exercise is what will give us more equatorial branches. Because all three of these have the same bulkiness, so it's not that one of them, they're all equally bulky, so one of them wouldn't prefer to be equatorial more than the others. It's just a matter of how can we get the most equatorial branches possible. That'll be the most stable figure. And maybe the easiest way to think through this one is to draw the two possibilities and then choose the more stable one after you've drawn it. So let's draw another cyclohexane. You draw those two parallel lines. The one at the bottom slants a little further down, the one at the top slants a little further up. The end that points down, draw a dot going up. The end that points up, draw a dot going down. And then connect the dots. This is our second cyclohexane ring. I'm going to move these a little bit just so they don't interfere with each other. Okay. Now, let's create one cyclohexane ring, one possibility. Let's say this chlorine is axial. So down axial, where would that be? Well, remember our footings. The side that points up, that has axial going up. The side that points down, that has axial going down. We've decided that the solid wedge means going down. And let's just try having that chlorine axial. Let's see how that ends up for us. So if the axial down position, that's that one at the left. Okay, so if that's axial going down, this next one is going to be going up. So which carbon, it could be on either of those two carbons. Either way, you'll get the same answer. I'm going to do the one in the back because there's more drawing room there for going up. So this now has to go up. And on this position, up is axial because it switches as you go one to the other. If on one carbon it's axial down, on the carbon next door it's axial up. Next carbon, axial down, axial up, axial down, axial up. And so we can compare to that one that we drew earlier. You can see that if this is axial down, the one next door is axial up. Okay, I do this a little long. Let me just fill that in. There we go. So axial up. All right, finally, we have this methyl group also pointing up. Now, we said the axials alternate. So if we go to the next carbon over, the methyl group is pointing up. But if this is axial down, axial up, then the next one has axial down. And that means that if this methyl group is going up, it has to be equatorial. Because every carbon has one axial position and one equatorial position. The axial positions alternate, so axial down, axial up. The next one has to be axial down. And if it's axial down, then the up position has to be equatorial, because every carbon has an axial and an equatorial, pointing in opposite directions. So I'll get rid of that marker there, and so now we have our green methyl branch there. So that's one conformation for cyclohexane, for this cyclohexane. And we can see here that we have two axial positions, two axial branches, and one equatorial branch. So it's not looking too stable. We have a lot of the unstable position and only one of the more stable position. Okay, let's try drawing it the other way. We started the previous one by assuming that this would be axial, and so we drew it axial. What if, instead of axial, this carbon is equatorial? How would we draw that? Well, remember our guideposts. The side of the ring that points up, we have axial up. The side of the ring that points down, we have axial down. Now, this is pointing down, a solid wedge, so it's going to be pointing down. Before we did it axial, now let's do it equatorial. Equatorial down, that's over here. And the reason why that's the equatorial down is because if this is axial up, every carbon has an axial and an equatorial in opposite directions. So if this is axial up, then it's equatorial down. Okay. Now you might say, wait a second, I thought we were putting the chlorine on this carbon. How come we can just suddenly put it on this one? And you can do that because this is a three-dimensional molecule. Imagine taking this and swirling it around, like spinning it, like you might twirl a hat. If you spin it, if you rotate it around, then this carbon on the left in that molecule, this carbon ends up becoming that carbon. So you can draw them however you want. Because the molecule is three-dimensional and it's constantly tumbling and turning, what's important is that they have the same relationships. They're all right next to each other, and they're pointing in the same directions as are in the figure, relative to each other. Okay, so we've got here our first carbon, or chlorine, sorry, we have it equatorial, going down. Well, if that's going down, this next one must be going up, the one next to it. So here, I'm going to draw that here because there's more drawing space. Now, if that's next door and it's going up, it must be equatorial also, because it switches. If you have equatorial down in one place, it'll be equatorial up right next door. It alternates. You could see that in the figure we drew earlier. If it's equatorial down here, then it's equatorial up next, equatorial down, equatorial up, equatorial down. It alternates. So if we had equatorial down, right next door we'll have equatorial up. So we had down and then up. In this case, both equatorial. Now if this chlorine is equatorial up, then next door to it, the up position must be axial because the equatorial positions alternate. So if it's down, then up, the next one would have to be down. So this carbon is equatorial down. Every carbon has an axial and equatorial position that point in opposite directions. If this is equatorial down, then the axial position is the one that's pointing up. So we know that this methyl group will be pointing up, and it's going to be right next door to our previous carbon, so that right next door to that is going to be right here. And if it's pointing up there, it must be axial, because we already determined the equatorial position is pointing down there. And so that is the other conformation for this. Now notice, here we have two equatorial positions and one axial group. So we have only one axial and two equatorial. And so which one is more stable? The one with more equatorial groups. The one where the biggest branches, or the most branches, are equatorial. And so here, that would be this conformation on the right. That's the most stable conformation for this cyclohexane. The other one, this one, on the left, that is not the most stable. That is an unstable way for the molecule to exist. At room temperature, they actually reach an equilibrium, but the equilibrium will strongly favor the products. So you'd have more products than you would have reactants. Okay, let's try D. So first thing we want to do is to draw, let's draw the cyclohexane ring all by itself. Oops, that ring. And so when you draw cyclohexane from the side, you draw two parallel lines. The line on the bottom slants a little bit more down. The line at the top slants a little bit more up. The side of the lines that slant down have a dot going up. The side of the lines slanting up have a dot going down. And then connect the dots and the lines. So that's our cyclohexane ring. All right, now let's look at the branches. We have three branches here. We've got a methyl branch at the left. There's one carbon there, so meth, it's a branch, so YL. We have a methyl branch in the middle. There's one carbon, so meth, it's a branch, so YL. And here on the right, that's one of those weird branches that have common names. That is a tert-butyl branch. Those common names are names that you would just need to memorize. Okay, well, the bulkiest branch by far is the tert-butyl branch. It is the poster child for a bulky, crowded branch. You have three methyl groups all pointing together. If you try to draw all the hydrogens in, they just overlap. That's how messy, that's how overcrowded that area is. You can see it when you draw those hydrogens in. So what we want to do is we want to make sure that that bulky branch is equatorial. We want to make sure that it is pointing out into space, right? Because bulky branches are more stable when they are equatorial. So we want to make sure we draw that tert-butyl group as equatorial. Now remember our little rule of thumb. The side of the ring that's pointing up, that has axial going up. The side of the ring that's going down, that has axial going down. If we want the tert-butyl equatorial, we have to decide first what's going to be up and what's going to be down. And you can decide either way. You just have to be consistent. Let's make, here I'm going to choose that those solid wedges, which mean that the bond is coming out at you, those will be going down. If you put up, you'd still end up getting the same correct answer. It may not look the same, but you'd be able to twist the molecules in such a way that they would be the same thing. And if that is going down, then the bonds going away from us will end up going up. Coming out at us, going away from us, those are opposite directions. Down and up, those are opposite directions. Okay, so in this case, we want the solid wedges to go down. The tert-butyl is a solid wedge, so it's going to go down. And here, if we have it going down here, it will be equatorial. And we want it to be equatorial. It's equatorial there because every carbon has one branch going axial and one equatorial. We know the axial there is going up, so the equatorial has to be going down. Okay, I'm going to get rid of those guideposts. So we have that now. All right, next, we're going to go for the methyl. This methyl right here. Now that methyl has a solid wedge, so it's going to be going down. And it's right next door. Now you could go to either of these carbons. They'll both give you the same answer. Even if it doesn't look the same, it is the same if you move it around in three-dimensional space. So here, we'll look at this carbon in front. I'm going to choose that carbon in front because there's more room to draw there. And we want the group pointing down here. Remember, though, that the branches alternate. So if it's down equatorial on this carbon, then equatorial is going to be up on that carbon. They alternate. And if that's equatorial up, then the down position must be axial, because every carbon has an axial and an equatorial position going in opposite directions. So if the equatorial is going up, it's the axial that's going down. Well, down is how we wanted to draw this methyl group, because it has a solid wedge. And so we'd draw the methyl group as drawn here in that pink line. There's our methyl group going down. All right, next branch, we're going to have this last methyl group, and that is going to be going up for us because it has the dashed wedge, which we decided was the direction up. Now, that's going to be next door to the other methyl group, so here, and notice that the up position there is axial. And it's axial because the positions alternate. If it's down axial here, it's up axial next door. Right? If we look back at our model, you can see if it's down axial here, it's up axial next door. So, that is the most stable conformation for this molecule. Notice that if you drew the other conformation, you would have these as equatorial and this as axial. So you'd have more things as equatorial in the other conformation. But what you want to make sure is that the biggest, bulkiest group is equatorial, even if that means that the other things have to be axial. It's the bulkiest group that decides the conformation of the molecule, the most stable conformation of the molecule. So the tert-butyl group is the bulkiest group, so we had to make sure that was equatorial. Bulky branches are more stable when they're equatorial. And once we knew that that was equatorial, we figured out what the other two branches had to be. Okay, last but not least is this E. So E here, first we want to draw the most stable conformation of the molecule. Let's just draw the cyclohexane ring from the side. And when you draw a cyclohexane ring from the side, you have two parallel lines. The one on the bottom slants a little lower down, and the one at the top slants a little higher up. The side that's going down, draw a dot there going up. The side that's pointing up, draw a dot there going down. And then connect the lines and the dots. Okay. Now, remember our guideposts. The side of the molecule it's pointing up is axial up. The side of the molecule it's pointing down is axial down. Those are just guideposts. So, let's have, now we just want to say the directions things are going in, just so we're consistent. It doesn't matter how we assign these, just so long as we're consistent. I'm going to put this as going up this time. If you have it going down, you'll end up with a molecule that's the same in three-dimensional space. If coming out at us is up, then going away from us, when we turn it to the side, will be the opposite direction, down. Okay. So, if we want, let's choose a tert-butyl group. Both of these branches are equally bulky. They're both really bulky. Both of them are tert-butyl groups. They're those weird common names that you just have to memorize. So those are both tert-butyl groups. And let's just choose one. They're both as bulky. One of them needs to be equatorial. So let's draw one equatorial. Now the one that would be going equatorial up, that would be coming off of this end carbon. And that's equatorial going up because every carbon has both an axial and an equatorial position and going in opposite directions. This had axial down, so it would have to be equatorial up. Okay, now that I have a branch on there, I'm going to get rid of those guideposts, and I'll use the branch that I have to guide me for the directions for the rest of the branches. Now, the other branch is going to be 2 atoms away. So here, this is the carbon where that's bonded to. It's going to be 2 atoms away. And I'm doing it in the back of the molecule. You could have just as well done it in the front. So for example, you could have just as easily, getting the same correct structure, you could have this as the pink and this as the orange. Both of those ways of drawing are the same correct molecule. Okay, so we want a tert-butyl group coming off of that orange carbon. Now, if this is equatorial going up, then this is going to be equatorial going down, and this will be equatorial going up. So in that orange carbon, we have equatorial going up, and we want the other branch to be going up because it has that solid wedge, which we decided at the beginning we were going to assign up. So we're going to have the other tert-butyl branch in an equatorial position. I'm going to get rid of that guidepost there. And so this is the most stable conformation of this molecule. It has both of your bulky groups in equatorial positions. And equatorial positions make bulky branches stable. So notice we had our bulky up, our equatorial up, and 2 away, the equatorial is also up. So hopefully that gives you a little better of a sense of how to take these cyclohexanes, draw them from the side, and take the bulkiest branch, or the largest number of branches, and make those equatorial. It's more important that you have the bulky branch, the most bulky branch equatorial than the largest number of branches. So first, look to see if you have a really bulky branch. If you do, one that stands out, it's extra bulky, make that equatorial. And if you don't, like we had here, then just try to get the largest number of branches to be equatorial. And the molecule, the conformation, the drawing that has the bulkiest branch equatorial, or the largest number of branches equatorial, that's the most stable conformation of that